Well, this video is for Math 60, and this is for the first assignment on algebra and solving equations. So first I want to talk a little bit about algebra in general, where it comes from, what it does, and how it can be useful. So algebra has a history that goes back several thousand years. I think the Mesopotamians in the Middle East were using algebra, 3,000, 3,500 years ago, something like that. And they mostly had what are called algorithms, or a series of instructions for how to calculate something. It was mostly examples, worked examples, but the numbers, it was clear, were interchangeable, and all of those instruction lists ended with the phrase, "This is the procedure." And so it was the procedure that they were focused on, and not really the numerical aspect of it. So that's how the Babylonians approached algebra. The Indian mathematicians had similar algorithms for methods of calculation and solving of equations. The more contemporary mathematicians in the Middle East, well, I say contemporary, I'm talking about 800 AD, so this is now 1,200 years ago. So that's where the word that I used, algorithm, a few minutes ago, actually comes from the name of an Islamic mathematician, It's hard for me to spell that on the spur of the moment without looking it up. I'm not sure exactly where this H goes, but in any event, his name was Al-Khwarizmi. He lived, I believe, in Baghdad in the 9th century or so, and he was well known for a book that he wrote about algebra. And actually, one of the phrases in the title of that book is where our word for algebra comes from, algebra. It has to do with the trading back and forth that we do on opposites, either sides of an equal sign. I'll talk more about that in a few minutes. So these are really old ideas, and it's not that they're old and useless, it's that they're perennial. They have been around and been a part of human societies for thousands of years, literally thousands of years. And multiple societies all over the world have found these ideas to be useful. Okay? Let's see here. What else do we want to talk about here? So in any event, the Arab mathematicians that I was talking about, Al-Khwarizmi, and his textbook that he wrote in the 9th century, that was mostly what is often called rhetorical algebra. Okay, so it's algebra where everything is written out in words. They didn't really have a symbolic process the way that was developed in Europe in the Renaissance, essentially. Okay, so those ideas from the Middle East were transferred into Europe in the Middle Ages. A mathematician known as Fibonacci published a book right around the turn of the 12th century there that was called Liber Abaci. And a lot of it was about calculation, okay? Because at the time, Europeans were still using Roman numerals, and there's nothing especially terrible about Roman numerals, except that they're really difficult to calculate with. I don't know if you've ever tried to multiply, 147. Let's see here. So 147 times 12 in Roman numerals. It's difficult. Okay? So what Fibonacci wrote about in his book Liber Abaci, and this also came from India and the Middle East, were what are called the Hindu Arabic numerals, which today we just call numbers. And the source of these symbols that we use to represent numbers is really kind of lost to us because they're so familiar, okay? But it's important to remember that there was a time when Europeans did not use this number system, okay? They used this number system, and they had they used an abacus or a counter, accounting system to tally things up. In fact, the counter in a merchant's shop often had place values where you could put little, like if there, if you had 104 tens, you could put 1 in the hundreds place and 4 counters in the tens place and so on, and that's where they would tally things up, is on the counter. And that's where we today still find the cash register to tally things up in a store, is on the counter. Fibonacci wrote this book in 1200. He introducing the Hindu-Arabic numerals into Europe along with the methods for calculation that we learned in elementary school. This was the cutting edge of mathematics in Europe in the year 1200. And in addition to the calculation methods, he also had the methods of algebra. Okay? And so once that information was introduced into Europe, now this was a handwritten manuscript, right? The printing press hadn't been invented yet. It was also, if you look at the title, it was also written in Latin. Okay? So it took a while for this to disperse, this knowledge to spread in Europe. But Italy is the origin of what we consider to be European mathematics, okay? Because of Fibonacci. In the 1400s, shortly after the invention of the printing press, they printed up something that's called the Treviso arithmetic, which was all of this stuff, but written in Italian and printed up on a printing press. And that's when European mathematics really took off. And gradually, these ideas spread, into France and Germany and England, and then all of those mathematicians that you may or may not be familiar with in France, Germany, and England, like Leibniz and Newton and René Descartes, Pierre Fermat. So all of those people come later on during the Renaissance. Okay, so there's a little bit of history of where algebra comes from, and it's really useful in solving problems, okay? And I'll talk more about that when we're running through some examples. I'll talk about the difference between the methods, learning the method of solution versus just getting an answer, okay? And those are two different things, and sometimes we just want an answer. Believe me, I understand that. But in other situations, there's no way to find an answer without using the methods. So it's a balancing act. And now that I've said that, let's talk about exactly what's going on in an algebraic expression. So in Europe, during the Renaissance, Europeans developed a symbolic algebra, okay, where the x is used to represent an unknown quantity. Let's see, let's pick a simple example here, x plus 4 equals 10. Okay, so the equal sign was developed from geometry as two congruent line segments, because the person said, well, what could be more equal than two congruent line segments? So that's where the equal sign comes from. Okay, so what this is saying, every equation has two sides, and we're stating the equality or the balance of those two sides. A lot of times I like to draw this picture right here of a two-pan balance beam with the equal sign as the fulcrum, and you've got x plus 4 over here and 10 over here, and those two things are in balance because they are equal to each other. Okay? So the process of algebra that comes from that Islamic or the Arabic root word aljabar has to do with trading back and forth between the two sides. Okay, and so the idea here is that if we want to know what x is equal to, rather than knowing what x plus 4 is equal to, well then we can take away 4 from both sides so that everything stays in balance. If we just took 4 away here, this would be too heavy, the two sides wouldn't be in balance. So what we want to do is we want to take away 4 on both sides and see that x equals 6. Okay, and so in our balance, set up here, take 4 away from both sides, and now we can see that the x and the 6 are in balance with each other, so x equals 6. Let's see. Oh, right. So that's the method. That's the method of solution, is to keep these two sides in balance. Whatever you do to one side, you have to do to the other side. Now, having said that, I was talking a minute ago about the methods versus the answers. So in some situations, there's this thing that mathematicians call solution by inspection, right? Where you just look at this and you're like, oh, something plus 4 equals 10. Well, 6 plus 4 equals 10. That's fine, okay? If all you need is the answer, that is fine. But what I'm really teaching is the methods, okay? Now, if you are in a situation where all you need is the answer, that's great. Just get the answer, okay? But in many situations, it's really challenging to get the answer if you don't use the methods. And I've been in both situations myself, you know? I've been in situations where I just need an answer and I do it the simplest way I possibly can. And I've been in other situations where I really need to pay attention to what's going on and carefully work through the methods of solution. Okay, so now that I've just erased that, actually I do want to put that back up for a minute here. The x plus 4 equals 10. And this equation has two sides to it. And we want to take the 4 away on both sides. And so we're left with x equals 6. Now notice here I did the opposite. This 4 was being added, so to cancel it out, I subtracted it. Okay? And so this goes back to our order of operations, right? If you want to cancel out something that's being added, you'll have to subtract it. If you want to cancel out something that's being subtracted, you'll have to add it. Next, addition, multiplication and division. If you want to cancel out something that's being multiplied, then you'll be doing dividing. If you want to cancel out a division, you'll be doing multiplying. And we won't do too much of this, but we do eventually, if you go on into Math 70 and Math 95, you may see these, okay? Where if you want to cancel out an exponent, you can take roots on both sides. And if you want to cancel out a root, you can raise both sides to a power, okay? So this order of operations, this hierarchy of operations, I think is really, really useful in a lot of different ways. And so it's a good thing to keep, you know, fresh in your mind as to how this works. All right, let's see. I think it's time to look at some examples here. And I put a bunch of different ones in here to try to point out mistakes that people often make. The first one is pretty straightforward, problem 2. We've got x minus 7 equal to 7. Okay, so what's happening to the x? That's always the fundamental question. What is happening over there with the x? We're having 7 subtracted from it. If we want to cancel that out, if we want to get the x by itself, then what we need to do is add 7 on both sides. This makes 0. Like when I put a slash through there, the reason I'm doing that is because that equals 0. I could just write like x plus 0 equals 14, but that's kind of redundant. You know, people don't really do that. And so all we do is we cross out the plus 7 and minus 7, we just say x equals 14. Okay? All right, let's see here. Problem 4, 4 plus y equals negative 10. Okay? Let's see here. So this was a this is a plus 4, so if I want to undo a positive, I'm going to need to subtract. Okay, so those cancel out and make 0. The positive 1y is left, and negative 10 minus 4, negative 14. All right, let's see here. What else? Problem 10. We've got negative 3.8 equals a minus 1.2. So now the variable's on the other side. It's on the right-hand side. There's nothing special about that. It doesn't really make any difference. I could actually just rewrite this as a minus 1.2 equals negative 3.8. These say exactly the same thing. There's nothing wrong with either one. So don't be freaked out if you see the variable on the right-hand side versus the left-hand side. Okay, so again, what's happening to this a? You can see we're subtracting 1.2 from it. So to cancel that out, we're going to want to add 1.2 on either side, right? We've got to keep things in balance. Sometimes I see people adding twice on the same side. That's not really helpful. That's not going to work, okay? The whole point of adding something to both is adding or subtracting something is to add or subtract it once on each side so that you're keeping everything in balance. That's the whole point. Okay, so these cancel out and make 0. We're left with an a here. And then over on this side, let's see, we've got negative 3.8, positive 1.2. You've got a calculator, go ahead and use it. But you can also look at it yourself and then check yourself on the calculator, right? So that looks like it should be negative 2.6 there. Okay. Let's keep going with these. I think in this first assignment, we're just going to see one-step problems. Okay? When we get to the next couple of assignments, we'll see more complicated problems. But for these will mostly be one-step problems. All right, let's see here. Problem 12. Got x plus 7 equals 2. And again, this is pretty straightforward. And that's what I like to do when we're starting out with something, is just to start out with the basic ideas, give you a little background on the concept, get the fundamentals, understand the fundamentals, and before we move on into more complicated things. So if you find yourself bored with the first assignment of a new topic, that's okay. All right, believe me, just be patient and things will get more complicated. Okay, let's see here. So in problem 12, again, we've got two sides of the equation here. We want to cancel out this 7 that's being added. So we're going to subtract 7 once on this side, once on this side. Those cancel out and make 0. And over here, we'll get x equals negative 5. So this is where, I mean, there's nothing so terribly tricky about that problem, but for people who are uncomfortable with negative numbers, it might be less obvious. Like when you see this one, you might think, oh, 6 plus 4 equals 10. But when you see this one, like I said, if you're not comfortable with negative numbers, this might be a little bit more tricky, okay? And in fact, equations like this, right, where there's no negative numbers in the equation, but the answer is a negative number, actually play a fundamental role in mathematics in exploring new types of numbers, right? Because you've got your positive numbers, then you've got the negative numbers. And then you've got the whole numbers, but then you've got the fractions, right? And then you've got fractions, but then you've got irrational numbers, like the square root of 2, which kind of fascinated Greek mathematicians because it couldn't be written as a fraction. So, like I said, these methods, I think, are important and also really useful in understanding, finding solutions, and also understanding the nature of our number system. Yeah, problem 14 is a good example. just like problem 12, we've got x plus 12 equals negative 4. And so again, you know, if you can solve this by inspection, wonderful. All right. If you find it a little bit confusing, then let's fall back on the methods, right? This is a plus 12, so we're going to subtract 12 on both sides. And so this will make 0, and this will say x equals negative 16. Right? Now remember when we were doing the integers, if this is 0, let's say this is negative 10, negative 20. Right? So we're out here at negative 16, and then this says add 12. Oh, okay. And that brings us back to negative 4. All right? So that's one way of sort of visually checking on this answer. Okay? All right. Let's see what else we've got. I think we're coming up to the multiplication and division problems in just a minute here. Okay. Now let's do one more, problem 16. And this one says 6 plus y equals 4. And remember, and like we were talking about during the combining like terms assignments, how the sign for a term, whether it's a numerical term or whether it's an algebraic term, is always in front of it, right? If there's nothing in front of it, that means it's positive. So this y is positive, and so is the 6. So if I want to cancel out the 6, I'm going to need to subtract 6 on both sides, and we'll just get y equals negative 2. Okay, so I think that's good for the addition and subtraction problems. We'll talk more about this when we get into those more complicated problems, the multi-step problems. But for right now, let's take a look at the multiplication and division problems. Okay, so first of all, remember that this is division, right? I use a fraction bar to represent division. Okay, so that means divided by. So anytime you see a fraction bar, that means whatever's on top is being divided by whatever's on the bottom. All right, let's see here. So, problem 20. We've got 56 equals 8y. So, when you see 8y like that, that means 8 times y. If you remember some of that substitution that we were doing in previous examples, right? This means 8 times y. So if we want to undo the multiplication, right, because we want to get the y by itself, so that means we're going to have to cancel out this 8. So to do that, to undo the multiplication, we're going to divide. And so, right, there's 2 sides to the equation. And so we want to do this on both sides. We want to divide. That actually is an 8. It's a little sloppy. There we go. Divide on both sides by 8. Okay. Now remember, when we had that x plus 4 equals 10, and I subtracted 4 on both sides, I canceled these out because they were equal to 0, and it was the same as saying x plus 0 equals 6. And so instead, we just said x equals 6. So that's, for addition and subtraction, when you cancel something out, it becomes 0. Now watch what happens here. In multiplication and division, when I cancel these 8's out, now I can just cross them out, but what's actually happening here is 8 divided by 8 is 1. Okay, 56 divided by 8 is 7. And so this is what we're saying here, is that we're saying 1y is equal to 7. That's like saying x plus 0 equals 6. It's not wrong, but it is non-standard. Mostly, we just say y equals 7. Okay? And this has to do with the nature of addition and subtraction versus multiplication and division, right? Because x plus 0 is the same as x, and 1 times y is the same as y. So that's what we're doing here when we cancel out with addition and subtraction versus when we cancel out with multiplication and division. All right, let's see here. So that was problem 20. Problem 22 says 12x is negative 84. And so again, we're going to do the same thing here. We want to cancel out this 12 that's being multiplied by the x. And so we're going to divide on both sides by 12. These cancel out. They make 1x. And over on this side, go ahead and use your calculator. I think this is going to come out to be negative 7. Okay, problem 26 says 4x equals 17. Same process, right? This is really the same type of problem in all three of these. The 4 is being multiplied by the x, so we want to divide on both sides by 4. These cancel out to make 1, and we get x. Now you can leave this as 17 over 4 if you want to. I know some people feel uncomfortable about what are called improper fractions. Maybe it's the word improper that makes it seem wrong, but there's nothing wrong with it. If you're a fan of decimals, you can just do 17 divided by 4 on your calculator, and that should come out to be 4.25. And I don't really have any preferences for fractions versus decimals. I think I've talked about this before. The only thing is if you run into a repeating decimal, like if you've got 3x equals 1, and I would say x equals 1/3, if you want to express this as a decimal, be sure to put a bar over the repeating part. Okay? All right, let's see what else we've got here. Okay, so that was 26. Well, let's go ahead and talk about problem 30 here. So, problem 30 says 2/3 x equals 10. Now, so I've written it like that. You know, I have I've got the diagonal fraction bar here. On the assignment page, I've used the vertical fraction bar like this. And you can also sometimes see it as like 2x over 3 equals 10. These are all the same thing. They're all saying the same thing. So something that's important to understand is that this x is not down here with the 3, right? Okay, and I think that's why I use the vertical fraction bar on the assignment, is because this is a little ambiguous. Okay, all right. So let's use the horizontal fraction bar. There we go. Equals 10. Okay, I'll leave this up here for a minute, and we'll talk about that afterwards. Because, like I said, now these two are exactly the same, right? If you think of this as 2 over 3 times x over 1, right? Then that's how you get from here to here. Okay, so let's think of this as exactly the same as those previous problems we were doing. 2/3 is just a number, and we're multiplying that number times x. So, if we want to cancel it out, that means we have to divide on both sides by 2/3. And so this is the way I see a lot of students complete these problems. If you're doing the calculations on a calculator, that's frequently an easy way to go. Okay, so these cancel out. 2/3 divided by 2/3 is 1. That leaves you with 1x. Over here, 10 divided by 2/3. If you calculate that, you should get 15. Now, when I was in school, we didn't use calculators much up until like trigonometry or algebra 2 or something. So the way I learned how to solve this was to cancel out this 2 over 3 is to multiply by the reciprocal, 3 over 2. Okay? Because now the 3's cancel and the 2's cancel, and that makes 1x, right? And also, if you made this calculation, 10 divided by 2/3 by hand, the process is to multiply by the reciprocal, right? And so that's where we get the 15. So that's another way you can think of it. Now, if you think of the x as being up there with the 2, instead of being off to the side, then you can multiply by 3 on both sides, right, to cancel this part out, because this 2x is getting divided by 3. So to cancel that out, we want to multiply by 3, and that'll leave us with 2x equals 30, and then we divide on both sides by 2, and x equals 15. And you can see this is exactly the same as what I'm doing here. Multiplying by 3 and dividing by 2 gives us this answer of 15. Okay, so 3 different ways to do the same thing. Some people wish that I would just talk about one way to solve the problem, but different people have different strengths and weaknesses, and whichever of these methods makes the most sense to you, then that's the way that you should approach the problem. I don't want to just tell you one method if that's not your preferred method, you know, even if it is my preferred method. I mean, to me, that is like one of the most beautiful things about mathematics is that you do have these choices. You can choose to take a different path, but end up in the same place. All right, let's see here. We've just got a couple more problems. Now, problem 32 is kind of interesting here. So I think before I do problem 32, let's go back to problem 24, which I skipped over, but I realize now has an important concept in it. Negative 60x equals 360, and then let me put problem 20 up here just to remind us. 56 equals 8y. Okay, so here's the most basic idea of solving an equation using multiplication and division, right? This 8 is getting multiplied by the y, so to cancel that out, we want to divide by the 8. This makes 1y, this is 7, and so we just say y equals 7, because 1 times y is y, right? Okay, now over here is where sometimes people get confused. So the negative 60 is being multiplied by the x. So if we want to cancel that out, we have to divide by negative 60. Okay? Why? Is because our goal right here is to get this 1y, or in this case 1x, right? So if we divide on both sides by negative 60, negative 60 divided by negative 60 is 1. That's the whole point. Over here, we get a negative 6. Okay? So, why am I making a big deal of this? Well, one of the common mistakes that I see people make here, when you've got a negative in front of the variable like this, is people confuse this with the addition and subtraction procedure, and they say, oh, I've got to use the opposite sign here. I've got to divide by positive 60 on both sides, because that'll cancel out the negative 60. It doesn't, okay? If you divide negative 60 by positive 60, that'll give you negative 1x equal to 6, okay? The whole goal is to get a positive 1x. If you wanted to finish this off, I mean, this is something I was saying a minute ago about taking a different pathway. I haven't done anything wrong, okay? What happens is that people make this mistake and then they say x equals 6. And that's not true, because this is not positive 1. This is negative 1. And so if we want to finish the problem, you've got to divide on both sides by negative 1, and there's our answer, x equals negative 6. So, what I'm saying is if you see a negative in front of the coefficient, right, this number right here is called the coefficient, you've got to divide on both sides by a negative. These negatives cancel each other out, leave us with positive 1. Okay, so that whole discussion there was as a lead-in to problem 32. that k is getting multiplied by negative 2/7, that means I want to divide on both sides by negative 2/7, right? Those will cancel out and make a positive 1k. That's what we want. Over on this side, looks like we're going to end up with negative 28. And again, you can calculate this on a calculator. Be careful when you're dividing with fractions on a calculator. A lot of times you're going to need parentheses, okay? Whether your calculator uses that symbol or whether it does this symbol. You need parentheses around this 2/7 because if you just type in 8 divided by negative 2 divided by 7, you're going to get something different. Okay? So be careful when you're dividing with these fractions and using those parentheses to kind of isolate that fraction symbolically can be really important. So, and if you have troubles with your calculator, be sure to let me know. Okay. All right, so that's problem 32. Let's see what else we've got here. Problem 34. Here we've got y over 7 equals 2/3. So here the y is being divided by 7, right? That's what I was saying before, is that this means divided by. So the y is getting divided by 7, so that means we need to multiply on both sides by 7, or 7 over 1. So these cancel out, give us 1y. Over here, we've got 14 over 3. And if you like decimals, that's 2.6 repeating. No, that's not. What is it? 4. There we go. 4.6 repeating. Yeah. Okay. Let's see here. One more. Problem 36. And then I think we're done. Okay. Problem 36. 5x equals negative 2/5. And again, if we want to divide on both sides by 5, right, to cancel this out. Again, you can do this on a calculator, but again, be careful. I think this one, calculators have less trouble with if the fraction is what's getting divided into rather than what you're dividing by. But I think it's always good just to err on the side of caution. Put your fractions in parentheses if you're going to be using them on a calculator. Okay, so these 5's cancel out and make 1x. Over here, don't think that you can do canceling over here because it looks more complicated than that, and it is more complicated than that. Okay, this is going to turn out to be negative 2 over 25. Or, if you're a fan of decimals, I believe that's going to turn out to be negative 0.08. Alright, okay. Just one last thing about this last problem here, 5x is negative 2/5, is if you want to think of this as multiplying by 1/5, right, dividing by 5 and multiplying by 1/5 are the same thing. And so these 5's cancel out and leave you with x. And here's your negative 2 over 25 over here as well. Okay. All right. So there's the first assignment on algebra. And you can see there are a lot of these ideas of order of operations and computation are within this topic as well. And I think that the best math curriculums, you will see that. Okay? It's not like you're going to learn something and then forget about it for the rest of the term. It's like when you learn something, we're then going to use it in the next topic, and we're going to do that continuously so that you get to practice everything. To me, that's a big deal, because if you learn something and don't practice it, it's more likely that you'll forget it. Okay, so as always, if you have any questions on this, please let me know, and we'll see you next time.